This boat has more than her name in common with the American spaceship. That Voyager 2, 2,700 million kilometers from the Earth, is controlled by exactly the same means as is the boat, a few paces away. Radio, of course.
Juliet Charlie, receiving WSC 106.
A policewoman talking to base is like Goon Hilly communicating with a satellite, or the satellite with you, if it comes to that. Your personal radio works exactly like a ship's radio.
We'll be going alongside at 1700 to pick up stores.
Or an aircraft's.
We'll descend now to 200 feet on the radio.
And that part of your telephone link that doesn't use cables uses radio.
Mrs. Jenkins will be there at...
Either just locally, within the house, or over great distances, with a sort of microwave link that might also be bringing you your television pictures. Whatever example of radio we choose, it will involve communicating by radio waves between a transmitter and a receiver. And those radio waves are made up of two different types of field. Let's look at each in turn. Here is a coil of wire connected to a battery via a switch. Bring in a compass, and as we switch on and off, the compass deflects. The coil must be producing a magnetic field. Now let's bring in another coil with a meter across its ends, but not connected to the first coil in any way. When we switch the first coil on and off, the meter on the second deflects. The field from the first coil is producing a current in the second coil. Communication across space. But it only happens when the first coil is being switched on or switched off, when the field is changing, not when it's steady. This is a different case. This time it is an electric field at work, often caused by adding or subtracting electrons between materials. Nature can generate very large electric fields, which can break down the insulating properties of air and cause immense currents to flow. Here's another example of an electric field. This plate is connected to a high voltage supply. This one is connected to a sensitive meter. Bring the two plates together, leaving a gap between them. Now, when we make and break the supply to the first plate, the meter on the second plate deflects. The charge on the first plate causes an electric field to form in the gap. This field moves the electrons in the second plate, making the meter deflect.
I'm Bungle. Who are you?
Radio waves are a combination of those two fields, magnetic and electric, moving through space.
Yeah, I do.
This is a radio transmitter and receiver in a simple form. This is the transmitting aerial, consisting of two aluminium rods called a dipole, connected to a high voltage supply. When it's switched on, it produces a spark across the gap in the dipole. This causes an intermittent current to flow in the rods and across the gap, producing magnetic and electric fields around the rods. The receiving dipole is connected to a meter, and when it's brought near to the transmitting dipole, a current flows, showing that some sort of radiation must be passing across space from transmitter to receiver. But rather than using random sparks to produce the change in current in the transmitting dipole, we can use a controlled, high-frequency oscillator, which works even better. What does the radiation consist of? Well, of two fields. A magnetic field around the rod and an electric field parallel to it. As the current in the rod rises and falls, forwards and backwards, the two fields build up at right angles to each other. Together, they make an electromagnetic wave, moving out from the aerial. Radio waves and light waves are electromagnetic, and in a vacuum, they travel at the speed of light, 300 million meters per second. At the receiving end, there is obviously a current being produced. This is because the process now works in reverse. The wave arriving at the receiving aerial moves the electrons in the dipole to form a current, which registers on the meter. So, going from transmitter to receiver is a radio wave made up of two components. In your transistor radio, the aerial is a ferrite rod, which picks up mainly the magnetic component. But your television aerial works mainly from the electric component. Now let's look at another property of a radio wave. Suppose that this is our radio signal produced by an electronic oscillator. It rises and falls in a regular manner, and one of these complete sequences is called a cycle. The frequency is the number of cycles that occur in a second, and it's measured in hertz. By restricting a radio transmission to a single frequency like this, we can pick it out from all the other transmissions, which will have different frequencies. The distance travelled by the wave during one cycle is called the wavelength, and it's closely related to the frequency. Since the wave travels at a fixed velocity of 300 million meters a second, the more cycles there are in a second, the shorter the wavelength will be. In fact, the relationship is wavelength equals the velocity, 300 million, divided by the frequency. So it doesn't matter whether you refer to a radio wave by its frequency or its wavelength, as we can see here. These are the wave bands used for most radio transmissions. A kilohertz is 1,000 hertz and a megahertz is 1,000,000. Some bands are referred to by their wavelengths: long wave, medium wave, short wave, microwave, and some by their frequencies: very high frequency, VHF, and ultra-high frequency, UHF. Here it is on a radio: VHF, medium wave, long wave. But why all these different wave bands? The main differences lie in the way their radio waves get from place to place. The lower frequencies, long and medium wave, tend to hug the Earth and can therefore follow its curvature. This is called a ground wave. A long wave transmitting aerial, covering the world, might look like this. Long and medium wave receiving aerials used to look like this. But now they're more likely to take the form of a ferrite rod in a transistor radio. Shortwave can also go around the world by bouncing off an electrically charged layer called the ionosphere. This is called the skywave. Here's a shortwave aerial being used by a radio ham to talk to his friend in Australia.
Hello, CQ. Hello, CQ.
But shortwave is used for a large number of commercial jobs as well. VHF goes from place to place in a straight line, or with one bounce off the Earth. This is the space wave. To go long distances, it has to be relayed in stages. This is a VHF aerial used to pick up VHF FM domestic radio. The transmitter, or relay station, has to be quite near. UHF is very similar. It's the band used by colour television. And both VHF and UHF are used a lot by the police.
We move to hospital now.
The ambulance service.
Would it be convenient for details, please, over.
By aircraft and ships. And by cell net telephones. This one on a train. Microwave is normally line of sight only. Each microwave dish on telecom tower must be in line of sight with its equivalent on the next tower, and so on. This is how microwaves go long distances on the Earth. A ground station dish has to be able to see the satellite, as does a domestic dish. Well, that's fine. We've got a radio wave with its own frequency, and we know how it's going to get from A to B. But what can we say with it? As it stands, nothing at all. We could perhaps break it up a bit and devise some sort of a code. Mr. Morse did, of course. If we send a short, a long, and a short burst like this, we get dot dash dot. The letter R for radio. But since you can't hear radio frequencies, you need a special receiver to make the signal audible. There's a better way of sending information by radio. It's called modulation. This is our radio wave. We'll call it the carrier wave from now on. Let's suppose that this is the signal we want to send, a 1 kilohertz note. We can make the amplitude of the carrier, its strength, vary according to the 1 kilohertz note, like this. That is the radio wave we send out. At the other end, the receiver gets rid of the carrier wave, leaving us with just the note, audible on any radio. Now we can break up the modulation into Morse if we like, or into a more sophisticated train of pulses that can carry computer information or other data, or more complex signals for entertainment. Seen on an oscilloscope, this continuously changing waveform is speech.
And I've got a special announcement for you.
And this is music. They can also be modulated onto the carrier wave. This sort of modulation is called amplitude modulation, and it has a snag. Remember those sparks? Spark radiation, which causes interference, is mainly amplitude modulated, wherever it comes from, such as badly suppressed car engines and electrical machinery. Which means that amplitude modulation, AM, is too prone to interference for high-quality broadcasting. So for some radio systems, other types of modulation are used, such as frequency modulation, for hi-fi radio reception, and pulse code modulation for many microwave transmissions. These types of modulation are far less prone to interference. Let's finish by looking at the basic components of a radio system. The transmitter, on the left, is communicating with the receiver, on the right, by means of a radio wave. The first thing in a transmitter is an oscillator. This is what produces, at the required frequency, the waveform which is the basis of our radio signal, the carrier wave. The other important thing is the signal we want to broadcast, which may come from a microphone, a television camera, a tape recording, audio or video, a computer, or other source of pulses. This signal and the carrier are both sent to a modulator, where they're combined, giving us a signal to be broadcast. This is amplified to the strength needed to be transmitted by the aerial or antenna, which may be as big as this for the longer waves, or as small as this for UHF. The receiver starts with an aerial, of course, and thousands of radio transmissions on different frequencies are arriving at the aerial. So the first thing we need is a tuner to pick out the transmission we want. Tuning can be done by turning a knob, by pressing buttons, by infrared remote control, or by changing a crystal. The radio signal we've tuned is then sent to a demodulator, a device which removes the radio frequency that we don't need anymore, leaving just the signal we want. This is then amplified to make it strong enough to drive the output device, which may be a loudspeaker, a headset, a television screen, a visual display unit, a fax machine, the controls of this Voyager 2, or the controls of this Voyager 2.